Hello, welcome to the third lecture of the module micromechanics of lamina. We have been discussing the micromechanics approach for determination of stiffness and strength of lamina. Now, in the last lecture actually we have discussed in details the mechanics of material approach. Among different approaches of micromechanics, the most simple one has been the mechanics of material approach. So, in the last lecture we have discussed how to determine the engineering constants of a lamina like U1, longitudinal Young's modulus, transverse Young's modulus, in plane shear modulus and Poisson's ratios. We have also discussed in details the limitations of those mechanics of material predictions, and we understood that the mechanics of material predictions, while agree well in case of longitudinal Young's modulus U1, however, do not agree with the experimental results for the transverse Young's modulus, then the in plane shear modulus, because those are mostly matrix dominated properties. We understood the reasons also why the transverse stiffnesses do not agree well with the experimental results, mainly because some of the assumptions which actually do not go well with the matrix dominated properties like the transverse Young's modulus and in plane shear modulus. Therefore, there was a need for development of better and more accurate procedures to estimate the stiffnesses of the lamina which agree well with the experimental results, and therefore, efforts are made with different approaches like numerical approach, elasticity approach. Then in both in elasticity approach again we have already discussed there are exact elasticity solutions using the equations of equilibrium, compatibility and boundary conditions, and there are variational approaches using the principle of energy principles like minimum potential energy or complementary energy, and those provide upper and lower bounds on the stiffnesses or the properties of the lamina. However, all these approaches actually lead to, while numerical analysis like finite element method could actually provide better and more accurate predictions, but then this does not provide us closed form solution, and it is case specific. Say for a particular lamina with a particular volume fraction, we may get a better result using those numerical approaches like finite element modeling. However, it does not provide a generalized solution, and while the elasticity approaches actually tries to provide generalized solutions, but then it actually leads to a large number of complicated equations, sometimes curves, and they are not really very good for to be used by the designers because of two reasons. Number one, they lead to complicated equations, and secondly, these are for not generalized. It does not cater to a wide range of process variables like say volume fraction, different types of fibers and composites, different types of geometries, and therefore, there were inherent difficulties in using those by the designers. Therefore, there was a need to develop easy and some simple relations which are easy for the designer to be used for estimating the properties of, for estimating the stiffnesses of the lamina. So, semi empirical method actually came handy in that, especially the Halpinshine method, which actually provides relatively simple equations for estimation of lamina properties in terms of the properties of the fiber matrix and the relative proportions, and also even though it is actually approximate, but it actually covers a wide range, that is it is more generalized, and therefore, it becomes handy for the designers to use those for estimating the properties of the lamina. Now, in Halpinshine model, the longitudinal strength and longitudinal stiffness U1 is EF VF plus EM VM, which is exactly same what we actually obtained in mechanics of material approach. Similarly, the Poisson's ratio or so called major Poisson's ratio mu 1 2 is also mu F VF plus mu M VM, which is also similar to what we have actually obtained in mechanics of material approach. However, for transverse properties, Halpin-Tsai semi empirical model, it actually interpolated some of the elasticity solutions and provided a simpler, much simpler estimate, where we could actually predict the transverse stiffnesses of the lamina. This is m by mm is this is the Halpin-Tsai model for determination of transverse stiffness, where m actually stands for the transverse stiffness E2 or in plane shear modulus transverse Young's modulus E2 or in plane shear modulus G12. Similarly, MF actually stands for Young's modulus of the fiber or the shear modulus of the fiber or the Poisson's ratio of the fiber, and MM is the matrix modulus, that means the Young's modulus of the matrix or shear modulus of the matrix or the Poisson's ratio of the matrix. So, and he has defined the term eta as this, where there is an expression zeta. This zeta is actually the measure of reinforcement of the composite, okay, which is also sometimes called the reinforcement factor, and the value of zeta is decided by fiber geometry, packing geometry, loading conditions, and this zeta is determined by comparing this ratio of the composite transverse modulus or the composite modulus to the matrix modulus with the value of eta, okay, and an exact elasticity solution. Even though this Halpin-Tsai model actually observed to have correlated well with a wide range of composites, but then it is approximate, of course, it is approximate, but it is simple, okay. It gives a much simpler estimate, and it is ready to, I mean, we could immediately calculate the transverse modulus, and it covers a wide range of process variables, okay. Unlike many elasticity solutions which are actually restricted to a very narrow band of the design regime, but the difficulty with the Halpin-Tsai relation is determination of this reinforcement factor zeta, and they have actually tried with many cases and proposed eta is equal to 2 for circular cross section of the fiber and eta is equal to 2 into A by B for rectangular cross section fibers, where this is A and this is B, okay. And using these values, they have shown for some cases that it could predict the transverse modulus, I mean, reasonably well in a wide range of process variables, okay. So, we understood the mechanics of material approach for determination of the E1, E2, nu1 to G12. We also understood the difficulty in mechanics or the drawback of mechanics of material approach in predicting the transverse properties or matrix dominated properties like E2, G12, and then handy Halpin-Tsai same empirical relation came handy in determination of the transverse modulus. So, in summarizing that determination of E1, E2, nu1 to G12, what we could understand is that the mechanics of material approach is simple, and it also predicts well the longitudinal Young's modulus E1. However, it does not, it fails to predict the transverse stiffnesses or mainly the matrix dominated properties like E2 and G12, okay. And elasticity solutions and numerical approaches, when they do provide more accurate solutions compared to mechanics of material approach, but then they are also restricted to a narrow range of the design regime, and then semi empirical relation provided by Halpin-Tsai actually provides a, though approximate, but provides a simple and more generalized solution for the determination of matrix dominated properties like E2, G12, and it correlates well over a wide range of process variables. So, in general we could see that the fiber modulus EF significantly affects E1, okay. Therefore, E1 is a fiber dominated property, okay. then matrix modulus EM and significantly affects E2 G12. Okay. And it has this fiber modulus has very little effect on E2 and G12. Okay. And the Poisson's ratio nu f and nu m has very little effect on E2, very little effect on E2 and no effect on E1. This is the what we understood from the discussions in the last two classes. Okay. So, having understood the mechanics of material approach and the semi empirical approach for determination of the stiffnesses, let us now go to another important topic of determination of the strength properties of a unidirection lamina using micromechanical approaches. Okay. We have already seen in our discussions on macromechanical analysis of lamina that an unidirection lamina has 5 strength parameters, okay, namely longitudinal tensile strength. Okay. These are all with respect to a unidirection lamina having material axis. One is the longitudinal direction, 2 is the transverse direction, 1 2 is the principal material direction axis. Okay. So, longitudinal tensile strength, then we have longitudinal compression strength, because strengths are also direction dependent, these are orthotropic lamina, therefore, longitudinal tension and longitudinal compression strengths are different. Then transverse tensile strength in direction 2 and transverse compression strength in direction 2, and we have in plane shear strength tau 1 2. Say for example, I think for a typical graphite epoxy lamina, this used to be, just to appreciate that how they are direction dependent, it is 1500 megapascal, this is around 1200 megapascal. Transverse tensile strength is for a typical graphite epoxy lamina is around 40 megapascal, and transverse compression strength is roughly 250 megapascal, and in plane shear strength is roughly 70 megapascal. We have discussed these things in details when we studied the macromechanical failure strength failure theories, and we saw that the transverse tensile strength is far less compared to the longitudinal tensile strength, because this is actually matrix dominated, okay, and this is actually controlled by the fiber. Okay. So, these 5 strength parameters could actually naturally the strengths of a lamina, I mean taking note of the fact that lamina is actually heterogeneous and it consists of the fiber and the matrix, therefore, the strength of the lamina will also be decided or influenced by the corresponding strength of the fiber and the matrix. And I mean the macromechanical approach will try to relate the strength of the fiber and the matrix and the relative proportion to the strength of the lamina, I mean all these 5 strength parameters of a lamina. In general, the determination of strength parameters are more difficult compared to the stiffness parameters, because they are more sensitive to some of the important factors like materials and geometric inhomogeneity, then fiber matrix interface, okay. Then fabrication process a key role in the on the strength, then environment, okay. The strength gets degraded due to sometimes due to change in environment. We have already discussed that in case of hygrothermal, in a hygrothermal environment, if the I mean the presence of moisture or increase or decreasing temperature, the strength might get affected, therefore, a strength might get degraded. So, determination of strengths is more difficult because it is more sensitive to all these parameters, therefore, it is important to have accurate theoretical and empirical model. Okay. We have discussed already that suppose we want to find out determine the strength of a as made lamina, suppose we have a lamina say it is say 60% volume fraction. By this time we know what is Vf, okay. 60% fiber and 40% matrix. We are really interested to find out what is its tensile, longitudinal tensile strength. What we do is we take this lamina, load it, okay, in tension along direction 1 in a tensile testing machine and plot the graph between stress and strain, both are of course in direction 1. Okay. So, this point at which it fails is nothing but sigma 1 T u, and the slope of this curve is nothing but u 1. Therefore, we could determine. Now, suppose we change the volume fraction from 60 to 50, again we have to do another test. Okay. If the material is changed from say glass epoxy to graphite epoxy, therefore, we need to it is a time consuming and cumbersome. We have already discussed this in details. So, therefore, it is important that we have prediction methodologies, accurate theoretical and empirical model where we could predict the strength of an unidirectional lamina in terms of the corresponding strength of the constituent fiber and the matrix. But having said so, experimental determination is always more reliable. Therefore, I think we have discussed in the beginning of the micromechanics model that whatever micromechanics procedures we do develop, there should be careful validation, it should be validated carefully with the experimental results before we could actually use them with confidence. Okay. To start with, let us first see the longitudinal tensile strength of a lamina. Okay. So, in general, a lamina which consists of a fiber and a matrix, okay, it consists of fibers and matrix with defined properties of course. Therefore, the fiber is actually comparatively more brittle compared to that of the matrix, okay. And therefore, in general to start with, when it is loaded, both fiber and matrix may deform elastically, that means obeying Hooke's law. Then the fiber still continues to deform elastically, but the matrix might deform plastically. This is what it is. Till this time matrix is linear. Okay. Now, matrix may experience plastic deformation, then both fiber and the matrix, fiber is linear till more time, and then after that this also deforms. So, this is the stage 3, and then fiber fracture followed by the fracture of the composite material, and then finally this is the stage 4. Okay. Stage 4, the fiber fails. The main objective of adding fibers to the matrix is that we make it stronger and stiffer. Therefore, when the fiber fails, that may be considered as the failure of the composite. So, this is the failure of the composite. Okay. At this point is the fiber failure. So, in the beginning, for both fiber and matrix might actually behave elastically, okay, and then fiber still behaves elastically for some more time, while the matrix may experience plastic deformation. This is stage 2. Now, both fiber and the matrix might experience may deform plastically, stage 3, and finally, the fiber fails, leading to the failure of the composite. Okay. Now, we assume that to determine the strength of a composite in terms of the strength of the fiber and the matrix, we assume that all the fibers are of equal strength and are relatively brittle. Okay. That is true also. Fibers actually show, if we load a fiber till its failure, it shows very little plastic deformation. Okay. So, we assume that the fibers are of equal strength. That is something it may not be achievable, because suppose in a lamina there may be very large number of fibers and the strengths are actually statistically distributed. It is unlikely that all the fibers will have same strengths, but for the simplification of this analysis, we assume that all the fibers are of same strength. Okay. And fibers and matrix are active only in the linear elastic range, that we are not considering the plastic deformation of the fibers or the matrix. Okay. And both fibers and the matrix are isotropic, homogeneous and linearly elastic till fracture. Okay. This is what it shows. Okay. Fiber and the matrix are elastic till its fracture. Okay. Now, if you look at this stress strain curve, fibers are far more stiff compared to the matrix. Therefore, this is the Young's modulus of the fiber. We have considered the fiber to be isotropic. On the other hand, the matrix Young's modulus is slope of this curve E m. So, naturally E f is far higher compared to E m. Okay. So, knowing the ultimate strength of the fiber, ultimate tensile strength of the fiber sigma f u, we could obtain the ultimate tensile strain at which the fiber fails, because we have considered the fiber to be elastic till its failure. Therefore, this is nothing but obeying Hooke's law. This is ultimate stress of the fiber at failure divided by the Young's modulus of the fiber. Similarly, the ultimate strain of the matrix at failure, again considering that till failure it is elastic and obeying Hooke's law. Therefore, the matrix ultimate stress is sigma m u. Therefore, sigma m u divided by the Young's modulus of the matrix gives us the ultimate strain of the matrix. Okay. So, with these assumptions, that means first that all the fibers are equally strong, okay, and they are brittle, and that means till failure it behaves linear elastically. Okay. Even the matrix also have assumed that matrix also till failure it is elastic. Okay. And we have already discussed in our previous lectures that if this is the stress strain relationship for the matrix and this is the stress strain relationship for the fiber, the stress strain relationship for the composite will be somewhere in between. In this case, this is the stress strain curve for the composite. Now, what will be the slope of this curve U 1, because we are considering the longitudinal tensile strength of the lamina. Therefore, the lamina is loaded along direction 1, this is direction 1, this is direction 2. Therefore, this is the fiber stress strain curve, this is the matrix stress strain curve. What will be the stress strain curve, slope of the stress strain curve of the composite will be decided by what is the volume fraction. We have discussed that in details in our last lecture. Higher is the volume fraction, the more this curve will be towards the fiber, lower is the volume fraction, more this curve will be towards the matrix. Okay. In the limit, if V f is equal to 1, that means all fibers, this is nothing but the fiber stress strain curve. If V m is equal to 1, that means no fiber, then naturally this is the matrix stress strain curve, and in between the slope of the curve will be decided by the volume fraction of the fiber, and the, because we know that this E 1 is equal to E f V f plus E m V m. So, for a given E f and E m, it is the value of V f which decides what will be the value of E 1. Okay. Now, with these assumptions, let us see how to approach the ultimate tensile stress or the longitudinal tensile strength of a lamina. So, we have a lamina which is actually, this is direction 1 and this is direction 2. Now, when we add fibers in matrix, the objective is that the strength of the matrix will definitely be improved and the stiffness of the matrix will also be improved. That means, addition of fiber to the matrix will lead to higher stiffness and higher strength. Okay. And the fibers being the main load carrying member, if the fibers fail, we consider that the composite fails, it cannot carry any load further. Okay. Now, if that be so, suppose this is the stress strain curve for the fiber and this is the stress strain for the matrix, and for a given volume fraction this is the stress strain curve for the composite. Now, when this composite or this lamina is actually loaded, if you keep on increasing load, when the strain reaches the ultimate tensile strain of the fiber fails, the fibers actually fail. Now, we have assumed that all the fibers are of equal strength, therefore, all the fibers will fail. Suppose if you consider a representative volume element with a one fiber, so that the volume fraction is maintained, and if you apply load along 1, if the fiber breaks, okay, if the fiber fails, then the whole composite has failed. We assume that the whole composite fails. Thus, at fracture, now we know, suppose this lamina is loaded along direction 1, suppose F c is the load on the composite. We have seen in our last lecture that the total load F c is actually shared by the fiber and the matrix. Okay. Now, this could be written as sigma c is the stress in the composite, A c is the area of cross section of the composite, is sigma f is the stress in the fiber, A f is the area of cross section of the fiber, sigma m into A m, where sigma m is the stress in the matrix, A m is the area of cross section of the matrix. So, we could write this as sigma c is equal to sigma f V f plus sigma m, taking note of the fact that for the continuous fiber with same length, V f is actually V f could be represented by A f by A c, and volume fraction of the matrix is A m by A c. Because the length is same, we could multiply both numerator denominator by length, and it becomes the volume fraction. Okay. So, now look at this stress strain curve. The failure condition is that when the fiber strain is sigma f u, that means at failure epsilon okay. At this point, what is the stress in the composite? This is nothing but the stress in the composite sigma c, because it is in the direction 1, we can write this is sigma 1. So, at failure, what is the stress? At failure, the stress is, what is the stress in the fiber? Because this is the strain, therefore, the stress in the fiber is sigma f u. V f is the volume fraction of the fiber. What is the stress in the matrix at this point? At this point, the stress in the matrix is strain multiplied by the Young's modulus. Now, the Young's modulus of the matrix is E m, because it is linear, therefore, the stress here is equal to E m into epsilon f u. Okay. So, we can write the sigma m as E m into epsilon f u into V m. Now, this is the stress corresponding to this strain epsilon f u, when the strain in the composite actually reaches epsilon f u. So, the stress in the composite is actually given by this. Now, because at epsilon f u the failure condition, this is the failure, therefore, the maximum load the composite can take at this point is nothing but this. So, we can write this as sigma t u, that means the longitudinal tensile strength of the lamina, and this is equal to sigma f u V f plus E m epsilon f u. Now, this V m could be written in terms of V f 1 minus V f. So, this could be written as sigma f u minus E m epsilon f u into V f plus E m epsilon f u. Okay. This is the longitudinal tensile strength of the lamina. What does it mean? This is the maximum stress the lamina could withstand. What is the condition? The condition is that as the fiber fails, the lamina is assumed to have failed. Okay. So, this is the expression for longitudinal tensile strength of the lamina. Okay. Now, this is the longitudinal tensile strength in terms of, now what are the longitudinal tensile strength is actually expressed in terms of what? In terms of the, you just look into it, that ultimate tensile strength of the fiber, matrix Young's modulus, ultimate tensile stress, strain of the fiber and volume fraction. Therefore, the longitudinal tensile strength of the lamina is expressed as a function of the corresponding strengths of the fiber and the matrix and the relative proportions. Okay. Now, let us understand that the objective of adding fibers is that the strength of the lamina, the fiber volume fraction is such that the strength of the lamina is more than that of the matrix. Okay. Suppose there is no fiber. So, the matrix ultimate tensile strength is, look at this stress strain curve. So, the matrix ultimate tensile strength is sigma m u. Okay. Now, as we add fibers to it, therefore, it is expected that the strength of the lamina will be more than that of the matrix. Now, how much more, that is of course decided by the volume fraction of the fiber. Okay. As you keep on increasing the volume fraction of the fiber, the strength increases. Okay. In the limit there is no matrix, it is the strength of the fiber itself, but that is not a lamina. Okay. But the limits are that V f is equal to 1 or V f is equal to 0. V f is equal to 0 means we did not add any fiber, and therefore, it is the matrix strength. If we keep on increasing V f, that means keep on adding more and more fibers, the strength will increase. Therefore, we should add fibers such that the strength of the composite, that means the longitudinal tensile strength of the lamina must be greater than the strength of the matrix. Now, just now we had the expressions for sigma 1 T u. If we put it here, what was the expressions for sigma 1 T u? Just let me go back to the last slide. This is the sigma 1 T u. Okay. So, if we put this here, that means if we put this here, sigma 1 T u is actually equal to sigma f T u, sigma f u minus just the last expressions what we have obtained, E m into epsilon f u into V f into V f plus E m epsilon f u. This was the expression for sigma 1 T u, with an assumption that as the fiber fails, that is the failure of the matrix, and this is the maximum tensile stress it can withstand in direction 1. So, this must be greater than the tensile strength of the lamina. Okay. That means, the fiber volume fraction should be such that the longitudinal tensile strength of the lamina is more than the tensile strength of the matrix. So, therefore, we could write that sigma f u minus E m into epsilon f u into V f is greater than sigma m u minus E m into epsilon f u, and therefore, the volume fraction should be greater than sigma m u minus E m epsilon f u divided by sigma f u minus EM epsilon FU. So, if the volume fraction is greater than this means it ensures that the longitudinal Young's modulus of the lamina, that means sigma 1 T u, will be more than the ultimate tensile strength of the matrix. If Vf is less than this, then addition of fiber will not lead to the strength of the lamina more than the strength of the matrix. Therefore, this volume fraction is called the V critical. This is the critical Vf critical. This is the critical volume fraction. Okay. Now, look at this stress strain curve. What does it this critical volume fraction actually means? As we have discussed that this is the stress strain curve for the matrix and this is the stress strain curve for the fiber. Now, where will be the stress strain curve of the composite is decided by the volume fraction. Okay. Now, this is the stress strain curve of the composite. Say for a particular volume fraction, this is the stress strain curve of the composite. Okay. Now, this is the stress strain curve of the composite for a particular volume fraction. Therefore, at failure, this is the point which is the ultimate longitudinal tensile strength of the composite. Now, you could clearly see looking at this diagram for a particular volume fraction. Okay. And you can clearly see that in this case the sigma 1 T u, looking at this graph, is actually more than sigma m u, because this is the sigma m u. Okay. Now, where will be the location of sigma 1 T u is decided by what is the slope of the stress strain curve of the composite. Now, we have already discussed that the more is the volume fraction, the more this stress strain curve of the lamina will be towards the fiber, less is the volume fraction, more it will be towards the matrix stress strain curve. Now, suppose for a given volume fraction, the stress strain curve for a volume fraction which is lower, suppose the stress strain curve is this for a given volume fraction. Okay. Now, if this is the stress strain curve of the composite for a given volume fraction, then at failure, that means at this strain, what is the sigma 1 T u for the lamina? This is the sigma 1 T u for the lamina for this particular volume fraction. Okay. Now, it is clearly visible from this curve that this sigma 1 T u is less than the ultimate tensile strength of the matrix, okay, which is not desirable of course. This happened because this volume fraction is actually less than V f critical. Okay. Now, what is V f critical in this stress strain curve? Suppose if we provide V f critical, now what will be the V f critical is of course decided by several parameters, like it will be decided by the value of the ultimate tensile strength of the matrix, then Young's modulus of the matrix, ultimate tensile strain of the fiber, tensile strength of the fiber, and based on this the critical volume fraction will be different for different values of this. Therefore, for glass epoxy it will be different, for graphite epoxy it will be different. So, depending upon the material properties it will be different. Now, in this stress strain curve, if we provide say for a glass epoxy, if we take volume fraction as the V f critical, then the curve will be like this. What does it mean? At this volume fraction, sigma 1 T u is equal to sigma m ultimate. Okay. So, this is V f is equal to V f critical. So, above V f critical, the strength of the lamina, the longitudinal tensile strength of the lamina is assured to be more than that of the the ultimate tensile strength of the matrix. If V f is less than V f critical, then the addition of fiber will not strengthen the composite. Okay. So, this is important, that we will always try to keep the volume fraction more than the critical volume fraction. Okay. Thus, to ensure that to summarize, to ensure that sigma 1 T u is more than the sigma m u, the V f should be more than V f critical. Okay. Now, for even smaller, we understood the significance of critical volume fraction for a very small volume fraction. Okay. For smaller volume fractions, what happens? Suppose we want for a given composite, we apply, we add fibers, say 1% fiber volume fraction. I mean, just I am taking an arbitrary example. Now, as we have discussed that, look at this stress strain curve, look at this stress strain curve for the composite. Now, where this is the stress strain curve for the matrix, this for the fiber, and where this stress strain curve for the composite will be, that is decided by the volume fraction. And we understood already that if the volume fraction V f is equal to V f critical, then the longitudinal tensile strength of the lamina is just equal to ultimate tensile strength of the matrix, and only when the V f is more than V f critical, the strength will be more than that of the matrix. Now, suppose the fiber volume fraction is very small volume fraction. Suppose we have, say this is the matrix, and suppose only one fiber, just as an example. Okay. Now, when it is loaded, the fibers are actually, because the number is less, the matrix actually dominates. So, when it is stretched, the matrix will be stretched and the fibers will be carried away along with the matrix. Therefore, the fiber will fail first. Okay. Suppose the fiber fails, this fiber fails. Now, once this fiber fails, suppose this is the fiber and this fails. Okay. The fiber breaks. Now, because the volume of matrix is much more compared to that of the fiber, volume fraction of the matrix is more. So, maybe the matrix can still take further load even if the fiber is not contributing. Okay. Now, what is the stress in the, what is the stress in the composite? The stress in the composite sigma c is equal to sigma f V f plus sigma m V m. Okay. Now, when the fiber fails, suppose there is one fiber, as in this example, when this fiber breaks, it cannot take part in the loading, only the matrix will be carrying the load. Therefore, the sigma f is equal to 0. Okay. Then how far this matrix alone can take the load? The matrix can take the load till the stress reaches the matrix tensile stress, okay, ultimate tensile strength of the matrix. That means, the stress reaches this ultimate tensile strength of the matrix. Okay. So, that means, the volume fraction is such that once I mean, if the volume fraction is low, what happens is that even if the fiber breaks, the matrix could still take the load, and it can take the load till the ultimate tensile strength of the matrix is reached. Okay. And therefore, the composite stress when the fibers break and the matrix, when the fibers break, sigma f is equal to 0. Therefore, the stress in the composite is sigma m u V m. For example, suppose there is, say, the fiber volume fraction is, say, 1%. That means, the 99% of the matrix, that means V m is 0.99 into the matrix tensile strength is equal to the stress in the composite, and this is the I mean, if the matrix alone is taking the load, this is the maximum stress the composite could withstand. Okay. Therefore, the composite will fracture unless the matrix tensile stress reaches, that means, even after the fiber breaks, the composite will fracture only when the matrix tensile stress, matrix stress sigma m reaches the ultimate strength of the matrix. And at this point of time, what is the stress in the composite? The stress in the composite is, because sigma f is equal to 0, therefore, sigma m u V m. Now, in order that this does not happen, that means when the fiber breaks, the composite is failed, that means the matrix cannot take further load. That means the strength, the longitudinal tensile strength of the fiber must be more than this. So, if we put the longitudinal tensile strength of the fiber, already we have derived the expressions. So, what was the expression? The expression for the longitudinal tensile strength was sigma f u minus E m epsilon f u into V f plus E m into epsilon f u. This is the longitudinal tensile strength of the lamina, where if the fiber breaks, if the fiber fails, the lamina fails, and if after the fiber breaks, if the lamina could still withstand the load, and this is the maximum load it can, maximum stress it can withstand. Therefore, in order that the composite cannot carry further load once the fiber breaks, this must be greater than sigma 1 T u must be greater than, okay. Therefore, and this is we can write as sigma m u into 1 minus V f. Therefore, sigma f u minus E m into epsilon f u plus sigma m u into V f must be greater than sigma m u minus E m epsilon f u. Therefore, in order that after the fiber breaks, the matrix alone cannot take the matrix alone cannot take further load, this V f must be greater than sigma m u minus E m into epsilon f u divided by sigma f u plus sigma m u minus E m epsilon f u. Okay. So, this is the minimum volume fraction. Please try to understand the difference between the minimum volume fraction and the critical volume fraction. Critical volume fraction ensures us that a fiber failure is the failure of the lamina. Minimum volume fraction, I mean if the volume fraction is more than critical volume fraction, fiber failure ensures the failure of the lamina, meaning that the strength of the lamina, longitudinal tensile strength of the lamina is more than the ultimate strength of the matrix, and the minimum volume fraction tells us that the longitudinal tensile strength of the lamina is more than the ultimate tensile strength of the lamina of the matrix multiplied by the volume fraction of the matrix. That means, in case a fiber breaks, the matrix, the volume of the matrix itself could withstand the load till the matrix tensile strength is reached. Okay. So, V f should be more than V critical to ensure that the longitudinal tensile strength of the lamina is more than that of the matrix. V f should be more than V minimum to ensure that the matrix alone, the volume fraction should not be such that the matrix alone can take the load in the event of the failure of the fiber. Okay. So, it is clear here again in the stress strain curve. If you just look at the stress strain curve, we have already seen that this is V critical, where the longitudinal tensile strength of the composite is just equal to the ultimate tensile strength of the matrix, and more than V critical, the longitudinal tensile strength of the lamina is more than the sigma m u, and less than V critical, the longitudinal tensile strength is less than sigma m u. Now, suppose it is further less, that means if it is here, say, that means V f is less than V f minimum. What does it mean? The tensile strength sigma 1 T u is less than the sigma m u into the volume fraction of the matrix. That means, whatever is the volume of the matrix remaining besides the fiber, they alone could take the load, and failure will occur only when sigma m reaches the sigma m ultimate. Okay. So, this is the significance of volume fraction minimum and volume fraction critical. So, what you could do is you take a maybe a glass epoxy and a graphite epoxy, and in the book you will find the properties of the glass and graphite epoxy, I mean graphite fiber, glass fiber and epoxy matrix, and you can actually calculate the values of V f critical and V f minimum, and you will understand that where they stand. Okay. So, these are the expressions for V f critical and V f minimum. Now, if we plot the ultimate tensile strength of a lamina, this is sigma 1 T u, considering the fiber failure as the failure of the lamina. So, this is the plot. Okay, we get this straight line. Of course, I mean at V f is equal to 0, this is nothing but sigma f u into E m, and at V f is equal to 1, this is nothing but the sigma f u. Okay. Similarly, we could also plot the ultimate tensile strength of the lamina, considering that the matrix could take the load even if a fiber breaks, and this is what we get. So, naturally when there is no fiber, then this is the ultimate sigma m u is the strength, and when all fibers, of course, this does not happen because all fibers does not make a I mean this is not a composite, but then it is 0. Okay. So, if you look at this below this is V minimum. Okay. That means, below this V minimum the tensile strength of the lamina is less than sigma m u V m, and above this, above V minimum, above V f minimum, sigma 1 T u is more than sigma m u V m. Okay. Then if we further increase the volume fraction, a point comes where sigma 1 T u is just equal to the matrix tensile strength, and above that, okay, above that in this regime sigma 1 T u, it ensures that the strength of the composite is more than the ultimate strength of the lamina. I mean longitudinal tensile strength of the composite is more than the ultimate tensile strength of the lamina. So, therefore, this part is matrix dominated, okay, and then this part is fiber dominated, the strength is dominated by the fiber. So, we could actually find out, say, for glass epoxy, we can take the properties of epsilon f u, then E f, then for the matrix E m, okay, and then sigma m u. Now, I mean knowing this, we can find out what is epsilon f u. This is nothing but sigma f u divided by E f. Okay. Similarly, knowing this, we can find out epsilon m u is nothing but sigma m u by E m. So, knowing these properties, we can actually find out what is V f critical. You may try this and what is Vf minimum. You will have a feeling of that what is the volume fraction, minimum volume fraction that should be provided in order that the first thing that the composite longitudinal strength is more than that of the matrix, okay, that is Vf critical. So, I will stop here today. Thank you.